Welcome to the Using FPGAs with the Intel OneAPI Toolkits online training. My name is Ogene Uriri. This is the first of a two-part introductory course on using OneAPI with Intel FPGAs. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the email address provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. The objectives of this online training is to get you familiar with the Intel OneAPI product, the data parallel C++, DPC++ language, which enables the OneAPI product, and the OneAPI toolkits for FPGA. This training also aims to teach you the development flow for FPGAs when designing with the Intel OneAPI toolkits. This online training will cover an introduction to the Intel OneAPI product, DPC++ language, FPGAs, and the development flow for using FPGAs with the Intel OneAPI toolkit. Let's now get started with the introduction to the Intel OneAPI product. To fully appreciate the Intel OneAPI product, we first take on the concept of heterogeneous computing. Heterogeneous computing refers to a single system having multiple architectures. It has become a fast-growing trend for achieving optimum performance in diverse workloads. The individual strengths of these architectures, such as spatial, vector, scalar, can be combined for the benefit of the overall system. These strengths, which range from performance, throughput, latency, I/O flexibility, memory bandwidth, can be combined. The advent of heterogeneous computing gives developers the ability to optimize, specialize, inline, and offload workloads to meet various business needs. Workload diversity continues to plummet, with more and more demand for hardware that can handle the diversity. However, no single architecture is best for every workload. Hence, the workload diversity is driving the hardware diversity. Therefore, it is safe to conclude that the future is a diverse mix of scalar, vector, matrix, and spatial architectures deployed in CPUs, GPUs, AI, FPGAs, and other novel accelerators. The growing trend of heterogeneous computing is not without its challenges. This is because you are dealing with multiple architectures limited by programming barrier. Today, you find that each architecture requires separate programming models and toolchains. The toolchains will typically need training and licensing to use them. You end up needing to have license and training for various compilers, IDE, debugger, analytics and monitoring tool, deployment tool, and many others for every architecture on the system. The challenges doesn't stop with licenses, but extends to even debug, monitoring, and maintenance of your cross-architectural source code. Some of these toolchains can also pose difficulty in integration across proprietary IPs and architectures. Plus, there is no code reuse. You prepare code per architecture you are targeting. These challenges also extend into the overall software experience, leading to software development complexity, which limits freedom of architectural choice. Thus, with heterogeneous computing comes this huge barrier to entry that makes it unappealing despite its numerous advantages. Only those with the resources to make isolated investments required for technical expertise can afford to take advantage of diverse architectures on single system. To address the programming challenges posed by multiple architectures, a unified programming model was developed called the OneAPI. OneAPI delivers a one-shoe-fits-all model to simplify development across diverse architectures, enabling users to take advantage of diverse architectures easily. This product provides a common developer experience across scalar, vector, matrix, and spatial architectures, which is deployed in CPUs, GPUs, AI, and FPGA devices respectively. It also guarantees an uncompromised native high-level language performance with industry standardization and open specifications. The Intel OneAPI product was developed with future developers in mind, providing a model that supports diverse workload efficiently. The advantages of this product is far too numerous. It goes without saying that you have one set of toolchain, libraries, language, and compatibility tool to handle all of your application workloads requiring diverse architectures. Developers can now have faster turnaround time as development complexity is drastically reduced using the inbuilt tools. For instance, you can iterate and complete proof-of-concept designs quicker through emulation and reports by performing functional verification and performance tuning respectively before having to perform a long hardware compilation, which typically takes several hours for FPGAs. You can get runtime data across your host and accelerators through the vTune profiler, plus easily develop complex hardware patterns implemented through macros, pragmas, headers, and other built-in language features. Using OneAPI model provides you an extensible code that is compatible with existing high-performance languages, such that you can now reuse source code across multiple hardware architectures and vendor platforms, although code will need optimization to be performant on a different architecture. Furthermore, the problem of barrier to entry is reduced with the commonality of sequential programming languages and IDE integration that you can leverage. This, of course, improves ramp-up and debug time for developers. Now that we have understood what the OneAPI product is, let's take a look at what makes up the product and what is essential for FPGAs, the accelerator this training is meant for. The Intel OneAPI product consists of data parallel C++, DPC++, which enables direct programming, a bunch of libraries that supports API-based programming, and of course, analysis and debug tools. DPC++, which is the programming language for OneAPI, is SYCL, maintained by Kernels and some community extensions. All of the source code you will develop for your design will be written in DPC++, a combination of modern C++, version 11 or higher, and SYCL 1.2.1 and higher. We will look at DPC++ in the next section. The OneAPI product also includes a DPC++ C++ compiler built on a CLang LLVM front end for RTL generation and a DPC++ runtime for resource allocation and management during execution. The OneAPI toolkit for FPGAs includes support for direct programming with DPC++ with the addition of analysis and debug tools. The general idea is to pair the value and flexibility of an FPGA with that of the OneAPI programming model. FPGAs are great for data-dependent parallelism workloads where spatial architecture and pipelining is the key differentiator from other architectures. FPGAs have programmable low-latency IOs for accelerator-to-accelerator and accelerator-to-host communication. FPGAs have flexible on-chip memory architecture that allows developers to create multiple banks for parallel read, write, or to move large amounts of data using a high bandwidth memory enabled board. By simply using OneAPI to target FPGAs as accelerator, we can take advantage of the strengths of FPGAs in targeting workloads and get efficient performance. For you to begin using the Intel OneAPI product with FPGAs, you would require a combination of the Intel OneAPI based toolkit, the Intel FPGA add-on for OneAPI based toolkit, and the board support package for the FPGA board you are targeting as an accelerator. We will learn more about this in details in subsequent sections. Now that we have been introduced to OneAPI, we will take on the next session where we will take a look at DPC++, the language that enables OneAPI, and get familiar with the fundamentals of programming in this language. Recall we mentioned that DPC++ is a combination of C++ version 12 and higher and SYCL version 1.2.1 and higher. SYCL is based on OpenCL. Now think of DPC++ as SYCL with some extensions. If you are familiar with OpenCL, you will find that there are some similarities with DPC++. A major difference, however, is that DPC++ allows for single source targeting of accelerators. Basically, you don't require multiple files when targeting accelerators such as GPU, FPGAs, etc. DPC++ is an industry standard with open specification. With DPC++, you have a common language that targets all XPUs, albeit some tuning is required depending on the architecture you are targeting. Driving the goal of OneAPI, DPC++ provides the language that incorporates everything needed to get the best performance out of every architecture. DPC++ has 3 scopes with which the compiler identifies what operation is being handed off to what device. As the developer of the program, it is important to be aware of these scopes so as to ensure you are getting the right functionality. The first scope is the application scope, which is your normal host code. Everything you can do in C++ can be done in the application scope. The host code runs on the CPU, which is typically the host for your design. As we can see in the example, declaring function pointers, setting up buffers, selecting devices are in the application scope. The second scope is the command group scope that kicks off when you submit something to the queue. The queue is the line of communication between the host and the acceleration device. We will discuss queue class shortly. This scope signals to the compiler that operation will soon be handed off to the acceleration device for execution. All the capabilities of C++ are supported in the command scope. The final scope is the kernel scope, which is kicked off within the command group scope. This scope is kicked off using the kernel dispatch command. In this example, we have a kernel dispatch command single task sent to an FPGA accelerator previously selected. Note that not all C++ capabilities are supported in the kernel scope. For instance, recursive code cannot be executed on the kernel. For a comprehensive list of the restrictions with C++, do well to check out the SYCL specification. The runtime is the program that is running in the background when you execute your model. It gets installed in the background along with other tools that you will need for setting up your system to run OneAPI. The runtime controls the execution and data passing to the heterogeneous device. It also handles the kernel and host execution in the order that is imposed by the data dependency. Runtime takes care of passing data back and forth between the host and device. It makes queries to the device, and so on. Think of the runtime as the layer your code interacts with. A note about Lambda functions. Lambda functions are unnamed functions and are quite common to C++ users. You will come across them in most of the example codes in this training and in our DevCloud tutorials. We use them to keep the code all in line without having to wrap it into a function. Thus, it takes the place of what will be a function pointer, keeping our samples short and simple. Two common constructs in DPC++ that require function pointers as arguments are queue submissions and kernel dispatch functions. When writing these constructs, you will find that Lambda functions are utilized instead of the function pointers. To get you familiar with them, a simple guide is presented in the code snippet as shown. The square bracket tells what you intend to capture from the function. We usually use an equal sign or an ampersand sign. The equal sign implies that you want to capture everything, but you want it passed by value. The ampersand means you capture everything, but you will be passing it by reference. In the kernel dispatch call, we use the equal sign when using the Lambda function because we are physically passing data back and forth to the device by value. Next is the regular parenthesis, which represents the parameters we are passing into the function. Objects like handler are captured in the parenthesis when we need access to the member functions of that object. For instance, the kernel dispatch is the member of the handler class, and we will make a lot of calls to it. So we do not just pass the handler, but we give it a short name to avoid writing handler out in full all the time. Lastly, we open a curly braces where we put the normal statements for functionality like in any C++ function. On a final note, Lambda functions are not compulsory. Feel free to wrap everything in normal functions and point to those in your own code. In the next couple of slides, we will look at some of the DPC++ class to enable us get an idea of how to write a DPC++ program. The device class represents the accelerators in a OneAPI system. These accelerators can be GPU, CPU, FPGA, and any other novel architecture. The device class provides member functions that we can use to grab some information about the device available to the host. For instance, using the function getInfo, we can find the name, vendor, and version of the device. We can also get the width for built-in data types, the clock frequency of the device, the cache width, and sizes, and whether the device is online or offline. You can have as many accelerators as you so desire, as there is no limit. In this example code snippet, we show how to make a query to see the devices that are available and get information about them. DPC++ also has a device selector class. This class enables selection of a device to execute kernels on. You can select a device of choice by using the selector construct described in the code snippet. You can also use the default selector, and the default device available will be used for acceleration. We use the device selector when we create a queue, as shown in the example snippet. See how we have selected the FPGA as the device for acceleration in the code snippet using the construct ext::intel::fpga selector. The comments in purple show how to make selection for other devices. Next, we will take a look at the queue class. Another DPC++ class is the queue class. It is the line of communication between the host and the device. It is a mechanism where work is submitted to a device. The queue submits command groups to be executed by the SQL runtime. Recall that the DPC++ command group scope is initiated with the queue.submit command. When this command is initiated, it signals to SQL runtime that groups of work is to be passed on to the accelerator for execution. You can have as many queues sent to a device. However, a queue maps to a single device. In the example code, we have declared a queue to a device with the selector and initiated the command group scope using the queue.submit command and capturing the handler class by reference using the Lambda function. The handler class contains all the command group functions of SQL. Next, we will discuss the DPC++ kernel class. The kernel, as we mentioned previously, is all of the code that we want to send off to the accelerator device for acceleration. The kernel encapsulates the code that will be implemented on the accelerator. Although the user does not explicitly construct the kernel object, however, when a kernel dispatch function is called, the kernel is constructed. The dispatch call for kernels are the parallel for and the single task. Using any of these functions constructs the kernel. In the example code shown, the kernel dispatch call is initiated by using the single task function. Notice that the kernel scope begins right after the curly braces is opened. Thus, the simple vector addition will be handed off to the accelerator device for execution. The single task kernels are those that are constructed with the single task dispatch call. These kernels allow complex, lengthy data paths to be built from custom hardware in FPGAs. They are useful when we intend to offload code with dependencies that are difficult to execute in a data parallel fashion. Since FPGAs shine in algorithms that are in this manner, this becomes the ideal and recommended kernel for FPGAs. When you glance at single-task kernels, they typically look like CPU code containing an outer loop to process all the data. The code snippet shows an implementation of a vector addition using a for loop in CPU. The corresponding FPGA implementation as a single-task kernel looks similar. We will be seeing many more single-task kernels as we continue in the training. The counterpart to single-task kernels is the parallel kernel. Parallel kernels allow multiple instances of an operation to be executed in parallel. The kernel is constructed when the parallel_for function is called. When you think of parallel operations, GPU comes to mind as the architecture allows for parallel execution of multiple instances. The parallel kernels, therefore, are best implemented on GPUs. Now, you can attempt to use a parallel_for kernel on an FPGA. While your operation will be functional, it will result in a less optimal implementation. The code snippet shows the same vector addition we looked at previously, implemented for CPU with the for loop. Take a look at the corresponding GPU kernel implementation using the parallel_for dispatch call for the kernel. Amongst other differences, notice that there are no outer loops as in single-task kernel for FPGA implementation. The final DPC++ class we will look at are buffers and accessors. Buffers encapsulate data in a SQL application in both devices and host. Buffers are data abstraction that represents one or more objects of a given C++ type. While a buffer itself is a single object, the C++ type encapsulated by the buffer could be an array that contains multiple objects. Buffers represent data objects rather than specific memory addresses, so they cannot be directly accessed like regular C++ arrays. Since a buffer object might map to multiple different memory locations on several different devices or even on the same device, for performance reasons instead, we use accessor objects to read and write to buffers. Accessors are the mechanism we use to access buffer data. The runtime is informed of how we intend using the accessors we create by the type of access mode we provide the accessors. In the example code, we create buffers for vector A, B, and C, and we create accessors A, B, and C to access buffers A, B, and C in a read-only, and write-only manner, respectively. The runtime determines data dependencies with the privileges or accesses we have given to the accessor we construct. It also uses this to determine the order in which kernel will be executed. Something else to consider when writing your DPC++ program is the necessary header files required to be included. Always include at the top of your program the cl/sickle.hpp header file when writing OneAPI programs and the cl/sickle/intel/fpga_extensions header file when writing programs targeting FPGAs. To make using classes less verbose, include the sickle namespace. Now that we have run through the fundamental classes for writing a DPC++ program, we will take a look at an example that will walk us through the basic steps in creating a OneAPI program targeting an FPGA as the accelerator device. This example code is a simple walkthrough of the DPC++ program. The first step in writing your DPC++ code is to create a device selector that will target the FPGA or whatever accelerator device you have in mind. To do so, we use the construct ext:/intel:/fpga_selector, all in lowercase letters. By doing so, we have successfully set up an FPGA device selector and let the runtime know that we want to use the FPGA accelerator. In the second step, we create a device queue. This is like setting up a line of communication with the acceleration device, which is the FPGA. We will pass data and kernel dispatches through this queue. When we establish the queue, we need to also tell it what device it would interact with. Hence, we pass in the selector from the previous step. The next step is to create buffers. We will be using the buffers to encapsulate data that we will be using later on in the device. We declare it with the keyword buffer. We give it a name and tell it what data we are encapsulating. In this example, we are encapsulating the pointers A, B, and C in buff A, buff B, and buff C respectively. Since the pointers don't have a size associated with them, we use a range in the buffer declaration because the construct for buffer requires that when we use pointers, we are to provide a range. The number 1 refers to the dimensionality of the range A, while N refers to the number of items that you are encapsulating. If you use a C++ vector, you won't require a range. Now to step 4. We submit something to the queue. This will also be the beginning of our command scope. To do so, we use the queue.submit command and we begin submitting what we want into it. Notice the Lambda function notation here, signaling that we are capturing everything and passing it by reference. The curly brace holds the actual function we want to execute. With the queue submission done, the next thing will be to hand off the necessary data that the device will be needing. To do so, we create accessors that will be able to access the data encapsulated in the buffers. Right in the command scope, we create the accessors A, B, and C for buff A, buff B, and buff C respectively. We also provide permissions or access modes for how we want to interact with the data. Note that these permissions are from the device's point of view. Accessor A and B are given read-only permissions. Accessor C can be written to. You can also provide a read and write permission for an accessor. Also, we hand the handler class previously established, hence the H in the parentheses in the construct. Now that we have successfully set up the FPGA as the device of choice and set up the line of communication and also buffers and accessors, we are ready for the final step, which is to dispatch the kernel. Still in the command scope, we create our single task kernel using the single task dispatch call. Notice the Lambda function at the dispatch call. Though Lambda functions are unnamed functions, we can give it a name. This really helps when we are looking at the report. We can tell what kernel the analysis is done for when it is named. In this example, the name vector add is given to the kernel. The code inside of the curly braces, which is the kernel, becomes part of the FPGA design and will be handed off to the FPGA for execution. Note that you can have multiple kernel scopes inside your program. That about wraps up the fundamental steps required to write your DPC++ program. The contents of buff C will be copied to the pointer C when the function finishes. This is because there will be buffer destruction of buff C upon completion. We will take a look at this later. Hopefully, this example has given you a good head start to how the DPC++ program looks like and how to get started on writing one for your design. We have mentioned earlier that the runtime determines which kernel to execute when we have multiple kernels. How it does this is by looking at how you are using the data you're accessing. In this example, we have multiple kernel scopes and they can all run at the same time. However, the runtime will first take a look at what permissions have been granted to the accessors, and with that information automatically determine execution ordering. Thus, if a kernel needs data that another kernel is producing, it will place an order dependency on that kernel. The example here shows kernel 1 is accessing buffer A, and it is doing so in a read and write manner, implying that kernel 1 is reading from A and also writing to A. This is represented in the graph. Kernel 2 is also accessing buffer A in a read and write manner. The runtime figures out that there is a dependency here. It has to wait on kernel 1 to finish writing into buffer A before kernel 2 can begin reading from buffer A. Looking at the execution graph, you find kernel 2 dependency is shown. Kernel 3 is accessing buffer B in a read and write manner. There is no need to wait on kernel 1 and 2, and hence the runtime knows to execute kernel 3 in conjunction with kernel 1 and kernel 2 at the same time. This is also indicated in the execution graph. Kernel 4 is going to be reading from buffer A and writing from buffer B. This means it must wait on A and B to get finished before the runtime kicks off executing this graph. In the execution graph, you can see that kernel 4 is waiting on kernel 2 and kernel 3. Its execution is the last before the program completion. The application scope, which is the host code, executes asynchronously to what is being executed on the accelerator device. Looking at the order in which the scopes are arranged, you typically go from application scope to command scope and then to kick off the kernel. However, when the kernel is dispatched and begin execution on the accelerator, whatever host code is after the kernel code continues running. If you need the host to stop and wait for the computations on the kernel to finish first before continuing to the host code, then you must impose the synchronization yourself. We will look at two ways you can impose this synchronization. The first way to impose synchronization is by placing an accessor in the application scope. So far, we have only used accessors in the command scope, which is from the accelerator device's point of view. Accessors created in the application scope are for the host. When the host accessor also points to the buffer the kernel is accessing, runtime creates a dependency node in the execution graph. In essence, blocking execution at the host until the data is ready. This example here shows an accessor in the application scope, and since the accessor is pointing to the same buffer that the kernel is accessing, the host has to wait until the kernel completes execution in order to access that buffer, thus imposing synchronization. The second way to impose synchronization is by declaring the buffers in their own scope. That is, creating buffers within a separate function. When execution advances beyond this function scope, buffer destructor is invoked. This causes data ownership to be relinquished and the data is copied back to the host memory. In this example, the buffer declaration and the queue submission has been put in its own function, void DPCPP code. The buffer declared in the kernel is within the function, meaning that before coming out of the function, the buffer has to be destructed. This happens because of the rules of C++. This has now placed the host on a hold for the kernel to complete execution. This form of synchronization can also be achieved by simply using curly braces around the buffer, although this isn't as friendly as it makes the code difficult to read later on. There is still so much to DPC++. We have bare